Hope you all had a good weekend. Hope you've had a chance to look at the homework. I think the homework is a little bit longer this time, just because we had more like individual topics last week than usual. So check it out. It's due tomorrow as usual. And just to make sure everybody is paying attention, next week on Friday is our first exam. So we'll talk some more about that. But yeah, a little something to look forward to. It'll take up the entire class period next Friday, so it'll be as if you're doing like a bunch of quizzes, I guess, one after another. I will actually like print out the test on paper and hand it out to everybody, and it covers everything that we've covered, including what we do this week will be on the test. All right. Anybody have questions about that at this point? We'll talk a lot more in detail about it as we go forward. All right. We, at the end last time, started talking about weighted voting, and that's what we're going to be focusing on for the next couple weeks. Weighted voting is all about situations in which, first of all, we are focusing just on voting for like yes or no answers to a question, or any situation in which there are just two alternatives, either, and usually I'm going to think of it as sort of a maybe a law or something that either it passes or it doesn't pass. That's how we typically think of this. And the way that a weighted voting system works, and also usually there's going to be a very small number of voters. Like this one here is a weighted voting system which has only 5 different voters. And when I write it in this way, the number you see first is called the quota. That's like how many votes do you need in order to pass the law or whatever it is. How many votes are necessary? There's like a threshold. Usually in the real world, the threshold is 50% of the votes of the voters, but that's not always the case. Sometimes you need a 2/3 majority or whatever. So we always begin with the quota first, and then over here, these numbers describe the weights of the voters. So in this example, I'm talking about 5 different voters, one with weight 12. That means when that person votes, their vote counts as 12. Another with 10, another with 5, and then 2 ones. All right, those are called the weights of the voters. And in order to get anything done in this particular example, you got to get to 20. That's how the law gets passed, or whatever it is that they're voting about. All right, this is the setup. And the big question that we're going to be asking is who has the power and how much? I don't know how much you remember from last time, but in this particular example, there are 5 different people here, right? And just taking a very kind of surface level view, you would say, well, obviously the 12 has the most power. And like these ones, they have the least power, all right? But, the ones have a little bit of power. The 5 has more than them, maybe 5 times as more, I don't know. And then the 12 and the 10 also have more. Actually, that analysis is not correct. In this particular example, we talked about this a little bit. In this example, we decided that the 12 and the 10 have equal power, and the 5, 1, and 1 each have no power, even though it seems like, those numbers aren't 0. But in order to do anything in this system, you got to get to 20, right? So the more complicated way of looking at this, that really you have to if you want to understand how the power works in this system, you got to look at these numbers, 12, 10, 5, 1, 1, and decide what are the various different ways that these numbers could possibly add up to 20. And if you think about it, well, the answer is, in order to add up to 20, you need to have the 12 and the 10, right? If you don't have both the 12 and the 10, you can't get to 20. And for that reason, actually the 5 and the 1 and the 1, they are totally irrelevant in this system. Whether they join in, even if the 5, 1, and 1 all join up with the 12, that only adds up to 19. There is no situation in which the 5 makes any difference one way or the other, and certainly also true of the 1 and the 1. That's why I said The 5, 1, and 1 each have no power. And also the 12 and the 10 have equal power. Even though 12 is a bigger number than 10, actually, just because of the way these numbers work out, there is no situation in which the 12 makes a difference more so than the 10 does. They're actually equivalent. All right? Any thoughts about that? So the moral of the story from the outset is you cannot just simply look at the numbers and say, yeah, 12 is bigger than 10. That means 12 has more power than 10. Because maybe it doesn't. All right? And you also can't say, the 5 has half as much power as the 10. Because actually, in this case, the 5 has no power at all. And the 10 has equal to the 12. So if you want, you can express this in terms of like percentages here. The 12 and the 10 have equal power. The others have no power. So the 12 has, you could think of it this way, 50%. The 10 has 50%. And then the 5, 1, and 1, they all have 0% of the power. This is like the true analysis of who has what power, right? And this is the kind of thing that we're going to be talking about for the next little bit. How can you make this kind of analysis? We sort of talked it out in this particular example, but it would be nice if you had some kind of specific way by which you could figure out these percentages, all right? And we are going to talk about, there are specific ways to do it. It's not exactly like a formula to plug into, because it's a little more complicated than that, but there is a specific procedure that we're going to talk about for figuring this out without, you don't have to think too hard about it, all right? Anyway, here's just another example. How about this? 30, 10, 10, 10, and 9. This is a somewhat, this is a similarly interesting example here. In order to pass the law or whatever, you got to get to 30. It looks like we have 3 people here with equal power and then 1 other person with slightly less. But actually, if you think about the way these numbers can add together, this 9, there's no way the 9 can make any difference. Because if you had, say, 2 of the 10s plus the 9, that only gets to 29. There's no way that this 9 can ever actually make it to the 30, right? Unless it was already 30 to begin with all 3 10s. So here, actually, the 10s have equal power. The 9 has no power at all, right? The numbers can be a little misleading here, right? That's all I'm trying to say. You have to have a keener eye than just looking at the numbers and seeing which are bigger and which are smaller. All right? Any thoughts? All right, let's get into it then. So first of all, I want to talk about some technicalities about which weighted scenarios are worth discussing. Actually, there are some specific examples that are not realistic in the real world. I mean, in theory, they could exist, but nobody would actually do weighted voting this way. For example, what if it was like this? This says the quota is 20. In order to pass the law or whatever, you have to get 20 votes. And we have 3 voters of weight 1 each. Anybody want to tell me why is this either unrealistic or just stupid for this to exist in the real world? Yeah?
There's no way to reach 20.
Yeah, these voters together, they cannot possibly make it to the quota. So this, you could do this in the real world. There's just no point for a system like this. This, I would say, is not worth discussing, right? So the problem here is the weights in this example. The weights are too small to reach the quota, right? And we're gonna disallow. We're gonna say that is not allowed in a weighted voting system. You might say you could do this in the real world, yeah, but it'd be stupid. So we're not going to talk about a system like that. The weights are too small to reach the quota. So in a weighted voting system like this, I'm going to use little variables for now. We're not going to do this very often, but just so that I can say specifically what I'm saying. If you have a system like this where you have a certain quota, which I call Q, and then a bunch of weights, W1, W2, up to Wn. There are a bunch of different weights over there. What's the rule about how this is supposed to work? I'm going to say for it to make sense, the W's, when you add them all up, they have to actually reach to the quota, right? Or be bigger. Usually they're bigger than the quota when you add them all up. So for it to make sense, I'm going to say it this way. The quota should be less than or equal to the sum of these guys. The quota is smaller than all the weights added together, all right? Otherwise, if the quota is bigger than all the weights added together, then that means they can never reach the quota, and this is a stupid system, all right? So in order for this to make sense as a realistic weighted voting scenario, the quota has to be less than or equal to. I hope you're all cool with this thing. This means less than or equal, right? I don't know about you. I remember when I was a kid, I had a hard time remembering which direction means which. I don't know if you ever have this feeling. The way my teacher told me was, I don't know if you've seen this. This one means less than because you can think of this as like the alligator, and the alligator eats the big thing. So the bigger thing is on that side. Anyone seen that before? I don't know. This is one of my teachers showed me this. That was fairly convincing to me. Although my teacher, this may confuse you if you're the type who gets confused about this sort of thing. My teacher also showed me this. They said, or you could say it's like this is like a little mouse that eats the small thing, right? The small thing is on the other side. The mouse likes to eat the small thing. But this, for some reason, when I was a kid, I didn't like that. Because I always found myself, if I encounter one of these things, I find myself wondering, yeah, but is that the gator or is it the mouse? Which one is it? The answer is, it doesn't matter which one it is. Either the gator faces the big thing. Anyway, nobody cares about this, right? Just remember, this means the Q is less than all the weights added together. Okay. What about something else? There's also a rule about. This basically says the Q cannot be too big. In this example, the Q was unrealistically big. There's also a problem if the Q is sort of stupidly small. Here is an example like that. So another issue, if the Q is too small, something like 2, 5, 5, 4, 1, all right? So here, the Q is kind of too easy to get to pass the law. Now, I don't know if that's really a problem in the real world. Sometimes people talk about, a certain vote you need 50% to win the vote. Or sometimes, like there are some rules in the Congress or in the Senate where it's like you need a 2/3 majority to pass the law. Has anybody ever heard of a rule where you only need 1/3 to pass it, like less than 50%? I have never heard of such a rule, although. Is that obviously stupid? Or, I mean, could you make such a rule? That, I don't know. Does it sound stupid to anybody? Yes? Anybody say why? Why is that stupid? To have a rule where in order to pass a law or something, you only need 1/3 of the people to agree. Yeah? Yeah, it's less than the majority. Is that a bad thing necessarily? I mean, maybe it's kind of like if I said, like, I'm not wearing a mask right now. The COVID is not entirely over. I could say, let's have a vote if we're going to all decide to wear masks or not. But I would make the threshold really low because I feel like, if there's even one or two of you who really wants to wear the mask, then maybe we should all go along with it. Is that a bad idea? I don't know if that's a bad idea in the case of masks. But for passing laws or whatever, they never put the quota less than 50%. I think one way of looking at it is here, let's say we can pass the law or whatever if, say, the 4 votes for it, even if the the 5, and the 1 are against. That's really the problem here, is that here, if the quota is too low, it means that the law or whatever can pass even if a majority are against it. And that for most purposes is sort of undemocratic, right? You don't want the law to pass if the majority of the voters are against it. And that's why, now my example about the wearing the masks is not entirely like that, because when it comes to wearing the masks and having a vote about that, I don't really care about being democratically just or whatever. But in the real world, making laws, usually you don't pass a law if a majority of the people are against it. Okay, so here, I'll just try and summarize that. If the quota is too low, it can pass even if a majority are opposed. And this you typically don't want to happen in the real world. So the rule for this one, like how low can the quota be then? So we're going to require the quota must be at least 50% of the total weight in the system. All right? And the way to 50%, 1/2, right? It has to be at least a half of the total weights in the system. And so the way to write that is the Q should be greater than, I'm going to write it this way. Writing inequalities, right? It should be more than a half of all the total weights. This ensures that you can't pass the law even if a majority are against it, all right? So this is the other rule for what the quota can be. The first one said the quota is less than something or other, and this says the quota has to be bigger than something or other. So the quota really needs to be in between these two values. We could say, we could write them together if you like. So I'm going to write them both as less thans. How about this? This has to be less than Q, and Q also has to be less than or equal to this. This is just a summary of the two things that I've said so far. So these are the two rules, or you could think of it as one rule about what the quota is allowed to be. It has to be in between those two things. It has to be bigger than half of the total weight, but less than or equal to the total weight. All right? That's just a little technicality about what the quota is allowed to be. The quota can't just be anything, because it will not make sense in a lot of cases. All right, any thoughts about that? All right, let's get down to some basic terminology then. Basic measures of power. And then we're going to talk about some more specific, more complicated, but there are some basic measures of power. For example, here's an example. 10, 12, 4, 2, 3. Now, what's interesting about this one, the quota is 10. The first voter, their weight is 12. So actually that first voter can make it to the quota all by themselves. All right? This is, you might say, a little unrealistic, although this situation does happen in the real world, say on a corporate board or something with people having different ownerships. It is possible for one person to just own more than half of the company, and then that means that one person already meets the quota which is necessary to pass any of the rules. So in this case, the 12 meets the quota all by themselves. If you ever see one of the weights bigger than the quota, then this is a very simple situation in terms of who has the power in this scenario. The 12 has all of the power, and these other people have no power at all. So 12 meets the quota all by themselves, which means the others have no power. All right. this is a simple scenario. If you ever see this first number bigger than the quota, then you don't have to say anything else. You can say that number, the 12, has all the power and everybody else has no power at all. There's a word for that, actually. We say the 12 is anybody want to guess? It's a word for the person, it's like the only person in this whole scenario who has any power is that person, and whatever they say goes. Yeah, they are called a dictator in this scenario. All right? So, and it's easy to tell if there's a dictator or not. You just look at the numbers, and if one of the numbers is bigger than the quota, that's a dictator. All right? Any number bigger than the quota. This is very easy to tell. Any number bigger than the quota is a dictator, all right? Can there be two different dictators? No, that doesn't really make sense for there to be two different dictators. Although you might think, going by the numbers, certainly like I could have written another 12 there. Wouldn't that be two different dictators? Actually, if you put two 12s here, then the total weights are too much. It would violate this inequality. So that actually will never happen. There will only ever be at most one dictator. Usually there's no dictator, but there may be a dictator. All right. So this is the first sort of simple thing to detect. If you see one of those numbers bigger than the quota, that one is a dictator. Everybody else has no power at all. Sometimes there's also a word for somebody with no power at all. For example, how about this system here? 30, 10, 10, 10, 9. Now, none of those 10s is a dictator because the 10s cannot make it to the 30 by themselves. So no 10 is a dictator. You could imagine maybe one of these 10s wants the law to pass, but the others vote no, and so it doesn't happen. So they don't always get their way, these 10s, right? None of the 10s is a dictator, but you can say something special about the 9. The 9 has no power at all. That is, there is no scenario in which the vote of this 9 makes any difference in this setup. So the 9 has no power at all, and there's a word for that too. It's kind of like the opposite of a dictator. The dictator has absolute power. This person has no power at all. When a voter has no power, they are called, I'm not making this up, a dummy. That's what they're called in this, in the theory of weighted voting. A voter with no power at all is called a dummy. It's a little bit more difficult to identify a dummy. A dictator is easily identified because it's just, if you see one of the numbers bigger than the quota, that's a dictator. But a dummy is harder to say. You have to kind of look carefully here and realize that there is no way that this 9 can have any contribution. All right? One thing you can say is if someone is a dictator, then automatically this means all others are dummies, right? Because if there is a dictator, that means that they have all the power and nobody else has any power, which means everybody else must be a dummy. But if there's no dictator, then it can be more difficult to tell who's a dummy and who's not a dummy. Here's an example. How about, this would be a sort of simple homework question. Is there any dictator or dummies here? Let's say 10. Oops. The quota is 10, and then my voters go 5, 4, 1, 1. Is there any dictator or dummies? The dictator is always easy. What do you say, yes or no? No. Dictator is just somebody who is bigger than the quota, and nobody here is bigger than the quota, so you can immediately say no dictator. That's because no voter exceeds the quota by themselves. Actually, I'll say no voter meets the quota. If there was somebody here who's equal to 10, that's still a dictator. It doesn't, strictly speaking, have to be bigger. It can be bigger or equal. Anyway, there's no dictator in this system. What about a dummy? You should be looking at the ones, right? And ask yourself, are the ones completely powerless here? Or are there some scenarios in which the vote of the one actually can make a difference? Anybody have a feeling? You feel like it is? Can you say, what exactly is the scenario in which the one would matter?
I mean, like, the one to get to 10.
Yeah, actually the ones are necessary in order to get to 10. But you can have, if you had, say, the 5 and the 4 were already going to vote yes, then it matters if this one is also going to vote yes, or if this one is also going to vote yes. So in this case, there are no dummies. This is because even the ones can contribute.
Can't only one of the ones contribute though? Like, isn't one of the ones a dummy? That's the only one of them.
Yeah, this is an interesting question. Let me just say what I was saying. The one is not a dummy because they can contribute. Like, you can actually add up to 10 in this way. 5 plus 4 plus 1 makes 10. And if you didn't have the 1 in there, then it wouldn't make 10. So the 1 really matters, all right? What she said is, but there's 2 of them. Maybe you only need 1 of them, right? Because if you additionally took the other one, that wouldn't matter anymore. It would add up to 11 then, and then you could have gotten rid of one of the ones. This is true, but we don't, when I say, is there a dummy or not, the question really is this 5 a dummy? The answer is no. Is this 4 a dummy? No. Is this 1 a dummy? The answer is no, because sometimes this 1 can make a difference. And also sometimes this 1 can make a difference. So you have to think of these, of course 1 and 1 are equal as numbers, but you have to think of these as if they were like 2 different people. Each of them had a weight of 1, and neither of those people individually is powerless. Each of those people can actually contribute to the results. That makes sense. I hope that makes sense. All right. Even the ones can contribute. All right. How about just same question, another example. How about, I have some of these for you to look at in a moment. How about 12, 9, 5, 4, 2? Is there a dictator? Is there any dummies? What do you say about dictators? Yes or no? No. Dictator is always easy. There's no dictator. That's because none of the voters make it to 12 all by themselves. No dictator. All right? What about dummies? You have to think more carefully about this. You should start by considering the 2, right? And you've got to ask yourself, is there any scenario in which the 2 can actually matter to make these things add up to 12? And I would just think about, okay, could I do, say, 9 plus 2? That doesn't make it to 12. What about maybe 9 plus 4 plus 2? Actually, if you do 9 plus 4 plus 2, that's 15, but in that case, you don't even need the 2. So the 2 was not necessary in that case. You have to just look at these numbers and decide, is there any way that the 2 can actually matter when you're adding them together? You could think of 5 plus 4 plus 2, that only makes it to 11. If you want to make it to 12, you could include the 9, but then the 2 doesn't matter anymore. I think the answer is the 2 is a dummy. All right, the 2 is a dummy. That's because there is no scenario in which adding these things together, including the 2, makes any difference. All right. What about the 4? Is the 4 also a dummy? I mean, you should. So the 2 definitely doesn't matter. Are there situations in which the 4 matters? Yeah? Can you tell me one? Like
9 plus 4.
Yeah, if you consider 9 plus 4, that makes it past 12 in a scenario where the 4 really is important. So 2 is a dummy. The 4 is not a dummy. This is because in 9 plus 4 equals 13, the 4 is necessary here. Or I'll just say the 4 is important. So there is some scenarios in which the 4 can make a difference. There is no scenario in which the 2 can make a difference. And then also, 5 and 9 are not dummies. Certainly, if the 4 is strong enough to make a difference, then definitely the 5 and the 9 are also strong enough to make a difference because they are more than 4. All right. So 2 is the only dummy in this scenario. All right? There's something interesting about this example. There's something special about 9 here. 9 is not a dictator. 9, that's just because 9 doesn't make it to 12 all by themselves. But I will have you notice, in order to get to 12, you must use the 9, right? Because these other ones without the 9, 5 and 4 and 2, they only add up to 11, which is not good enough to make it to 12. All right, so 9 is not a dictator because they don't necessarily get their way all by themselves. But if you want to get to the 12, you must use the 9. So there's a word for that. This is a little more complicated, but in this example here, the 9 can't make the quota on their own. But the 9 is necessary to reach the quota. All right, there's a word for this. If you think about what this means in the real world, is basically if the 9 says yes, that does not necessarily mean that it will happen. But if the 9 says no, it definitely will not happen because you can't make it to 12 without the 9. So here, I will say I'm just going to write what I just said. A yes from 9 doesn't force a yes result, but a no from the 9 does force a no result. Right? The 9 is not capable of passing the law or whatever by themselves, but they are capable of shooting it down. All right? There's a word for that in politics. Anybody heard of a scenario like this? That may be. I'm thinking of something else. You have to think of an appropriate word, which is also the same word that I'm thinking of. I know this is frustrating. In politics, they use this word. I know. I believe this is a word they use in the United Nations. This is called the veto power. It is somebody who, it doesn't mean they get their way all the time, but they do have the ability to shoot it down if they want to. So we say the 9 in this case has veto power. So I will just write, let me just write a definition of that. If some voter is necessary to meet the quota, that's really what we're talking about here. In that example, the 9 cannot get to the quota by themselves, but you have to use the 9 in order to make it. So if some voter is necessary to meet the quota, then we say they have veto power. All right. So these are the 3 sort of simple ways of looking at power in a weighted voting system: dictator, dummies, and veto power. The veto power is a little more complicated than the other 2. All right. So for example, in this one here, same example that I've mentioned a few times so far. 30, 10, 10, 10, 9. All right, we already said no dictator. And then the 9 is a dummy. What about veto power? Are any of these voters necessary in order to get to 30? Like for instance, this 10 here. Do you need to use this 10 in order to get to 30? I think the answer is yes. That means this 10 has veto power. And the same is true for the other 2 10s. All right, so in this case, no dictator, 9 is a dummy, and each of the 10s has veto power. Because you need each one of those 10s in order to make it to 30. All right. What about this? Simple variation. How about just add in another 10 to the same system? Now, in this system, it's still true that the 9 is a dummy and there's no dictator. No dictator. 9 is a dummy because it's still not possible for the 9 to make any difference here. What about the 10s? Do the 10s still have veto power? You got to ask yourself, when I look at this 10 right here, do I need to use this 10 in order to make it to 30? And the answer is no, because you could use the other 10s. All right. So in this case, none of the 10s individually has veto power. And you might find yourself wondering, well, yeah, but you do need, like any 3 of them you do need. That's not the question. When I talk about does this one have veto power, it means do you need this one? And the answer is no, you don't. You need these other ones if you don't have this one, but you don't need each individual one. So there's no dictator, 9 is a dummy, and in this case, there is no veto power. None of those 10s individually can prevent you from getting to 30. Yeah?
Can you just incorporate the example for 2 1s?
Yes, although that was about dummies. Sorry, I'm going to scroll for those of you who are writing. I'll go back to that. Like, that was this example, I think. The 2 1s, neither of them is a dummy. It's true. Actually, in this example, in order to get to the 10, you need to use one of these ones, but it could be either one, so neither of these has veto power either.
So can it be like 3 out of the 4 10s?
It's true. You have to use 3 out of the 4 10s.
Yeah.
But when I say who in this list has veto power, the answer is none of them individually has veto power. It is true that you need 3 out of 4 of them, but that's a different question. Yeah, you have to imagine these, when I write them like 10s, you begin to think of them as like interchangeable equal numbers. They are equal numbers, but they represent 4 different individuals, and none of those individuals are necessary to make it to 30 by themselves. All right, I got some for you to try. I'm going to give you just a bunch of different examples. Your job each time, just say if there are any dictators or dummies or veto power. This is a typical test question or whatever. I got 4 different ones here. And feel free to talk to your friends. Each time your job is to decide who is a dictator, if any, who is a dummy, if any, and who has veto power, if anybody. Your answer could be nobody, any of that. All right, 4 separate examples. I'm going to give you a few moments to think about it. I'm going to walk around to see how you're doing. Maybe I should have spaced them out a little more. I don't know. Sorry, there's a typo in the first one. Can you believe it? I don't know if anybody noticed. Here the numbers are too big. If you add them all up, you get like this 10 is less than half of the total amount here. So can we change the I'm going to change the 9 to 3. Then that won't be a problem anymore. Sorry about that. It probably doesn't make a difference to your answer. But, okay. All right. I think we're that is that I just changed the number.
Go ahead.
All right. Okay. All right. All right, let's chat about these. It looks like people are doing pretty good. So the first one, I think the first one is the easiest one because you can tell there's a dictator here. So the 14 is a dictator in the first one. And that automatically means everybody else is a dummy. So the 3 and the 1 are dummies. Is there any veto power? That means, is there any one of those numbers that we always need to use in order to make it to the quota? The answer is yes, it's the 14. So actually it is a fact that if there is ever a dictator, then the dictator is also automatically has veto power, right? Because the dictator means they always get their way. Veto power means they always get their way if they say no. And a dictator automatically has veto power. I hope everybody said that for this one. How about this one over here? Is there a dictator? No. The dictator is always very easy to tell. So there is no dictator here. None. How about dummies? Is there any number here which you can never use to get to the quota in an important way? Any thoughts? Yeah? Yeah, the 2, I believe, in this example is a dummy. Because there is no scenario in which you can add these numbers up to make 10 in which the 2 is important, all right? To get to 10, you could do, say, 7 and 3 and 2, but that actually adds up to 12, in which case you don't actually need the 2. So the 2 here is never important in any combination that adds up to 10. All right? Does anybody have veto power? That means, is any of these numbers necessary in order to make it to 10? You should be looking at the big ones first. Is the 7 necessary to make it to 10? I think the answer is yes. So the 7 has veto power. That's because you need to use the 7 in order to make it to 10. How about the first 3 here? Do you need to use this 3 in order to make it to 10? This is a little confusing, perhaps. I would say you do not need to use this 3 in order to make it to 10. You can use the other 3, all right? This 3, this is like I've been saying, you have to imagine these 4 numbers are representing 4 different people, and I'm asking you, is this person necessary to make it to 10? The answer is no, because the other one can make it. So the only one with veto power here is 7. I will just say for emphasis, not the 3s, all right? You need one of those 3s in order to make it, but not. It's kind of in a non-specific way. You don't always need. You have to imagine these 3s are 2 different people, Billy and Jimmy. You don't always need Billy because you got Jimmy instead, right? So neither of the 3s has veto power. All right. How about the this one here? No dictator. You can tell none of those numbers makes it to 10. None. How about dummies? You should be looking at the 2. You know, for dummies, you should look at the smallest ones first. Is the 2 ever relevant here? I think actually the 2 can be important. You can do 5 and 3 and 2. That adds up to 10. In which case, the 2 makes a difference in that specific scenario. So the 2 is not a dummy. So I'm going to say there are no dummies here also. Certainly, if the 2 is important in certain scenarios, then definitely the 3 is important, and the 4 and the 5 sometimes. All right. And what about veto power? What did you say? Anybody? Is there anybody who's necessary? Yeah. She said the 5 and the 4, or just the 5? She said the 5. I think I agree about the 5. I don't think I agree about the 4. You need the 5 in order to make it to 10 because if you took the other ones all by themselves, it would only add up to 9. So the 5 is necessary, but I don't think you need the 4 because you can do 5 plus 3 plus 2 and still make it to 10. So I'm going to say the 5 has veto power, not the 4, 3 or the 2. All right? And then the last one here, what do we get? No. So again, no dictator. That's easy enough. How about dummy? I suppose you should ask yourself, is the 2 a dummy? What do you say? I say yes. There is no way the 2 can matter here because you could go 7 and 2, that's only 9. You could go 3 and 2, that's only 5. Or you could do 7 and 3 and 2, that's 12, but then you don't need the 2. So the 2 is a dummy. Is the 3 also a dummy? We should also consider that. No, because the 3 can matter. If you do 7 and 3, then the 3 matters. So the 2 is a dummy, the 3 is not a dummy. And what about veto power? 7 and 3, I agree. The 7 is definitely necessary to make it to 10 because the other 2, 3 and 2, cannot make it to 10 without the 7. And similarly, the 2 and the 7 cannot make it to 10 without the 3 because they only add up to 9, 2 and 7. All right? What about the 2? Does the 2 have veto power? No, because the 7 and the 3 can make it without the 2. All right? This is how we analyze dictators, dummies, and veto power. Any questions about all that? These, you'll see some more of these on the homework. I think they're kind of cute. You should expect to do, one of these on the test, something like that. It's not too hard. You just got to know what to think about. All right? Excellent. What I would like to discuss for our remaining 25 minutes or so, I want to talk about specific measures of power in this kind of system. I'm going to say measures of like percentage of power. That would be the ultimate way of analyzing this. If you could just look at these numbers and say, yeah, the 5, maybe the 5 in this example, I'm just making this up. Maybe the 5 has like 50% of the power. Maybe the 4 and the 3 have 25% each and the 2 has 0%. Something like that. That would be the ideal way of producing an analysis of these systems. Specific measures of percentages of power. It turns out there is not just one way to do this. There's actually two ways to do it that we'll discuss, and there are others that we're not going to discuss. It's kind of like the voting systems. There's many different ways to do this. Two ways to do it that we'll discuss. This is kind of a theme in this class. Pretty much everything that we're ever going to talk about, there's going to be more than one way to do it. This is actually how mathematics in the real world tends to work, is that if you want to, certainly like just adding and multiplying, there's not more than one way to solve those kinds of problems. Problems like that, they have a specific answer that you get, and everyone can agree. But more complicated problems in the real world that you try to solve using mathematics usually have many different ways of approaching the problem and different ways of getting answers. So there's two ways to do it that we'll discuss. I'm going to say there are different methods that give, actually, there are different methods giving different answers. Like when you measure these percentages of the power, oftentimes if you do it the one way, you'll get some percentages. If you do it the other way, you'll get some slightly different percentages. Which one is correct? The answer is like, well, they're both just two different ways of measuring power. The sort of like spiritual notion of power is not a mathematical notion, so there are different ways of approaching it, and you're going to get different answers. But anyway, I want to talk about one today, and then we'll talk about the other one next time. Unfortunately, they're both named after people, and you just have to remember which one is which. Unfortunately, they don't have names which give you a hint about which is which. But anyway, the first one is named after two people. It's called the Shapley-Shubik. That's a K. Shapley-Shubik Power Index. This was invented by these people. Shapley and Shubik are two people's names. I don't really know anything about Shapley and Shubik. But they came up with this method by which you can measure how powerful each one of these different voters are. And the basic idea behind this is this is a little counterintuitive, but we're going to imagine the voters cast their votes in order, in some order, not necessarily in like numerical order, the biggest first, but they're just gonna imagine they're voting one at a time, which of course in the real world, well, sometimes you do votes one at a time like this. Imagine the voters cast their votes in some order, and as they're voting one by one, sort of the total number of votes is increasing every time. The guy with weight 5 votes, yes, so the total is now 5. And then maybe a weight 2 votes, yes, and now it goes up to 7, right? As the people are voting, the total gradually increases. The total will increase until it makes it to the quota, or maybe it never makes it to the quota. So the total will increase until it reaches the quota. Or not, right? And the idea behind the Shapley-Shubik is we count somebody as powerful if they were the guy who make it to the quota, all right? If you are ever the one who makes it to the quota, like your vote actually causes the total to pass the quota, that means you are important. And this is how the Shapley-Shubik approaches power. So I'm just going to write SS usually for Shapley-Shubik. Shapley-Shubik measures power by how often a voter is. There's a special name for this. The pivotal vote. What that means is theirs causes the quota to be reached. In that situation, they are called the pivotal vote, all right? Usually, like, the first guy who votes is not going to make it to the quota, but as more and more people vote, at some point, the quota is actually reached, and whoever that guy was who made the quota get reached, that is called the pivotal voter. And this is how the Shapley-Shubik measures power. For example, if one of the voters is a dummy, actually, if you think about what it means to be a dummy, it means actually your vote can never matter, which means you're never the guy who makes it to the quota if you're a dummy. And so, according to the Shapley-Shubik, your amount of power is 0 because you can never make it to the quota as the pivotal voter. This is kind of like, it's like sort of hitting the winning run in a baseball game or something. I can remember, this is a traumatic story from my childhood, not really traumatic. I was on like little league baseball teams when I was a kid, and I was always bad at baseball, but for some reason I still liked being on the teams. And I can even remember, I was old enough to remember this, that like my dad one year was like, "Hey, you want to play, are you really still interested in playing baseball again this year?" And I was like, "Yeah, I want to play again." And he was like, "Oh man," because I was always like the worst kid on the team. But there was one game I can remember where I actually scored. I was a pretty fast runner, so if I could get on base, then I was going to score. But I was a terrible hitter. I actually scored in this game, and then we ended up winning the game by 1 point. And after the game, the coach was like, "All right, everybody, let's all cheer for Jimmy," or whoever it was who actually scored the last run for us. We won by 1 point. The kid who scored the last run was like the hero of the day because that was the winning run. And I was just thinking, yeah, but I also scored, earlier in the game, but my run, don't I count for something? No. I still remember this moment. Anyway, this is what the Shapley-Shubik is based on, though. This idea of who is the guy, who is the kid who actually hit who actually scored the point that made us win the game. All right, that's what the Shapley-Shubik is all about, and we consider this. We measure who is pivotal among all possible orderings of the voters. This is because in reality the voters don't necessarily vote in any particular order. The ordering is a little bit artificial, and this is why I as a kid was uncomfortable with this kid getting so much attention because he just happened to be the last one who scored, whereas I was one of the earlier ones and I didn't matter at all. If you want to accurately judge how powerful all the kids were, you have to somehow consider all of the orderings to be interchangeable. And the way to do that is we're going to measure who is pivotal among all possible orderings of the voters. Anyway, let's just try a specific example here. I will show you what I mean. Let's say it's like this: 6, 3, 2, 1, 1, 1. All right, and for the sake of calculating the Shapley-Shubik, we're going to give names to these voters. Let's say I'll call them, and I'm always just going to call them A, B, C, D, E. Those are the names of the different voters. I hope this is not confusing. When we did our ranked elections, A, B, C were always the names of the candidates or the options you're choosing from. I'm going to call the voters A, B, C, D, E here. All right? And we have to imagine them all voting in a particular order. So let's say they vote in this order. There are many possible ways that you could order them, but I'm just going to make up a specific example. Let's say they vote in this order: B, A, C, D, E. All voting yes. And I want to know who is pivotal. Pivotat. Sometimes I write pivotat. I mean pivotal. Who is pivotal in that particular ordering? B, A, C, D, E. You have to look at this. Imagine they're voting in this order which one of them is the one who actually makes it to 6? And you have to sort of think this through a little bit. You have to think of it sort of step by step. Once you get used to this, you can do this all in your head, but the way you think of it is B by themselves is 2, all right? B and A, so when B votes, they did not make it to the quota. If it's B followed by A, that would be 2 and 3, which is 5. Still not making it to the quota. The next one, once C joins in, B, A, and C, this now adds up to 6, and the quota is met. So C is pivotal, right?
So will the problem tell you which order they're voting in?
No. So, well, in this case, the order really matters here. In what I can say is, in this particular ordering, the C was pivotal. All right. Now, when you actually do the Shapley-Shubik, like I said here, we're going to measure who is pivotal among all possible orderings. So the way you do this is you write down all the different ways you could order this, and then you count how often is C the pivotal, how often is A the pivotal. Right. That's where we're going with this. But
so everybody can be pivotal in all exams.
In some scenarios, different ones of the voters will be pivotal. Although, like, it's not necessarily true that they all could be. For instance, if one of the voters is a dummy, then they're never going to be pivotal because their vote can never actually be the one which reaches the quota. All right. Anyway, that was a particular example. How about so in B, C is pivotal in B, A, C, D, E, right? In that particular ordering, C is the pivotal voter. What about in C, E, B, A, D? You have to get used to doing this. It's not very hard, but figuring out who is pivotal in each of these orderings. I'm going to just copy this down here so that we can still see it. Who is pivotal there? So, would you mind if I try and do this one in my head? What I'm going to do in my head is add these values up as I go across. C, maybe I'll just temporarily write down what are the weights for each of these. C is 1, E is 1, B is 2, A is 3, D is 1, right? And as I go, I'm going to sort of read across these numbers from left to right, adding them together as I go, and see which is the one which actually makes it to 6 or above 6. Which one is it? I think it's the 3, right? The A. Because I go 1, okay, 1 doesn't make it. 1 plus 1 is 2, that's not good enough. Plus another 2, that's 4, not good enough. Plus a 3 makes it to 7, and now I am exceeding the quota. So the 3 here, the pivotal one is right there. All right, and so in this case, in C, B, A, D, C, E, B, A, D, the A is pivotal. All right, this is deciding who is the pivotal voter. All right. Like I said, let's just do an actual example where we're doing the Shapley-Shubik. The way to do it is you write down all possible orderings of these, which is sometimes a pain to do, and then you judge who is pivotal in all of those. So let me just write down the definition. First of all, some terminology here. Each reordering, we're going to call them, each reordering is called a voting permutation. That's a fancy word. Come on now. Voting permutation. Permutation is a mathematical word for like a rearrangement or a reordering or something like that. It's called a permutation. So each reordering is called a voting permutation. All right, and here's the definition of how you find the Shapley-Shubik. The Shapley-Shubik power index of some voter is the, you can write this as a percentage. More often we're just going to write it as a fraction. It's easier to express as a fraction. The Shapley-Shubik power index of some voter is the fraction of all permutations in which they are pivotal. So for example, if A is pivotal in half of all the permutations, then that's their Shapley-Shubik power index is 1/2, or 50% if you like it as a percentage. The Shapley-Shubik is the fraction of all permutations in which they are pivotal. So the way to do this is you list all permutations. Like I said, this can be a pain, but it's not so bad if there's only a few different voters. List all permutations, decide who is pivotal each time. And then you just make fractions. That's the easy part, is just to say what your answers are in terms of fractions at the end. All right? This is the setup. Let's just do one example, and I think that'll probably do us for today. This will take you a few minutes, although individually each step is not really very difficult. So let's do, here's an example, 16, 12, 10, and 5. And your job, find the Shapley-Shubik. All right, this would be a typical homework or test question. Find the Shapley-Shubik of this weighted voting system. So, first of all, you list out all the permutations. I'm going to call these voters A, B, C. I'm always going to call them A, B, C, D, whatever. I'm going to make a little chart here. I'm going to start by listing the perms. That's the possible permutations, all the different reorderings. It helps when I'm gonna write a list here of all the different reorderings. It helps to have some kind of system. I believe there are 2 which start with A, right? There's A, B, C or A, C, B. All right. There's also 2 which start with B. I'm gonna go B, A, C. How about I start with B and then I'll go like alphabetical order for the rest of them. And then the other one would be BCA, right? And then there's also 2 which start with C, and that's it. So there's CAB and there's CBA. It is a fact that with 3 different voters, there will always be 6 different permutations. You got to make sure you get them all. If you leave some out, then you're not going to get the right answers when you write your fractions at the end. Okay? And each time I have to decide who is pivotal. I think towards that end, it's helpful. You don't have to make this column in the chart, but to me it helps. I'm going to write the weights of those just in the same order. So A, B, C, the weights are 12, 10, and 5, right? A, C, B, the weights are 12, 5, and 10. B, A, C would be 10, 12, and 5. I'm just copying the weights of each voter. Now, when you're doing this yourself, you might feel like you can do one or the other of these columns in your head, and that's fine with me. You don't have to draw your chart the same way that I do, but I'm going to include as much detail as possible. CAB would be 5, 12, and 10, and then CBA would be 5, 10, and 12. All right, those are all the weights. And now, each time, we have to do that little thing that we were doing before. You go across this list of numbers each time, and you ask yourself, which one is the number which actually makes it up to 16, all right? So, in the first example, 12 does not make it. 12 plus 10 is 22, so the 10 is pivotal here. 10 is the one which actually makes it, so it's the 10 here. In the next one, 12 and 5, I believe 5 is pivotal in the next one. 12 by itself doesn't make it, but 12 plus 5 is 16. It's usually going to be the second one, at least in this example, it seems like. Is it always the second one? I don't know. 10 and 12, it's going to be the 12 that makes it to 16. How about the 10 and the 5? I think actually it's not the second one in that case, because the 10 and the 5 is still 15, which is not enough. I got to go to the last one, which is 12. All right? The next one, 5 and 12 makes 17, so it's 12. And the last one, 5 and 10 only makes 15, so I got to take the 12, which is the last one. All right? So in each in each row here, who was the pivotal? It was B here, C here, A, and A, right? Those are who's the pivotal each time. And now we're basically done here. The answer is, you summarize the answer as a fraction. So my final answer is A, B, C. Each one gets a fraction. A is going to be 4 out of 6. That's because I have 6 total permutations, and 4 of them are A's. So the Shapley-Shubik score for A is 4 out of 6. If you prefer, you can do this on your calculator. 4 divided by 6 is 66.6 repeating percent. If you like percents, you would do 4 divided by 6 on your calculator, and it's 0.666 repeating. B would be 1 over 6. This, if you like as a percentage, is 16.6 repeating. And then C is also 1 out of 6, which as a percentage is 16.6 repeating. Usually I wouldn't expect you to write the percentages, just because like on our quiz or something you won't have a calculator. I would say just leave it as a fraction. But if you care about percentages, you can do it on your calculator, on the homeworks, for example. All right, what this means is in this system, we can say very particularly the A has 2/3 of the power, 4/6, and the B and the C have 1/6 of the power each. Maybe this is surprising, but it's true if you think about these numbers. The 10 and the 5 actually have the same amount of power, even though 10 is a lot bigger than 5. And the 12 has much more power than either the 10 or the 5, even though the 12 is only a little bit bigger. All right, that's the Shapley-Shubik. We'll do more next time.